Bismillahirrahmanirrahim. In the name of Allah, the most gracious, the most merciful. Assalamu alaikum. Welcome to Physics Mathematics Hub. I hope you are all in the best of health. Let's begin today's video by seeking Allah's blessings. Today, we are tackling an exciting quantum mechanics problem from the renowned book Quantum Mechanics, Concepts and Applications by Nouredine Zettili. Specifically, we will be solving exercise 1.29 on page 75. So let's get started. Here's the problem. Calculate the ground state energy of the doubly ionized lithium ion obtained when one removes 2 electrons from the lithium atom. Part B. If the lithium ion is bombarded with a photon and subsequently absorbs it, calculate the energy and wavelength of the photon needed to excite the doubly ionized lithium ion into its third excited state. We are given only a doubly ionized lithium ion. We have to find the ground state energy of the doubly ionized lithium ion denoted by E1, energy of the photon for the third excited state denoted by E gamma, and that is equal to E4 minus E1, and wavelength of the photon for the third excited state denoted by lambda gamma. Before diving into the solution, let us first introduce you to the doubly ionized lithium ion. The neutral lithium atom has 3 electrons orbiting its nucleus, but when 2 of those electrons are removed, we are left with lithium 2+, which now has only 1 electron, similar to a hydrogen atom. Now this setup resembles the hydrogen atom as the ion has only 1 electron. However, there is a key difference. Instead of just a single proton, the lithium nucleus has 3 protons. This increased nuclear charge affects the energy level of the electrons. Now that we have a basic understanding of the doubly ionized lithium ion, let's move on to solving the problem. In part A, we will calculate the ground state energy of the given ion using the formula for hydrogen-like atoms. En is equal to minus Z square multiplied by R divided by 1 plus Me divided by capital M into N square, where En is the energy of the nth state, Z is the atomic number of the ion. In case of lithium, Z is equal to 3. R is the Rydberg constant and is given by the formula. Substituting all the constant, we get 13.6 electron volt. N is the principal quantum number. For the ground state, N is equal to 1. Me is the mass of electron, which is equal to 0.511 mega electron volt per c square. mass of the nucleus is equal to 3 multiplied by mass of proton plus 4 multiplied by mass of neutron is nucleus of the lithium contains 3 protons and 4 neutrons. So putting the masses, we get 3 multiplied by 938.27 mega electron volt per c square plus 4 into 939.57 mega electron volt per c square, multiplying 3 by mass of proton and 4 by mass of neutron, we get 2814.81 plus 3758.28. Adding both the terms, we get 6573.09 mega electron volt per c square. Now, the term in the denominator of equation 1 can be simplified as 1 plus mass of electron divided by mass of the nucleus of lithium atom. Dividing mass of electron by mass of the nucleus, we get 0.0000777. Simplifying this, we get approximately equal to 1. The negative sign of the energy in the equation 1 is due to the bound state nature of the atom. Or we can say that the states with negative energy corresponds to bound states. Plugging all the values in equation 1, we have E1 is equal to minus 3 square multiplied by Rydberg constant, which is equal to 13.6 electron volt, divided by 1 into 1 square. Simplifying the fraction, we get minus 9 multiplied by 13.6 electron volt. After multiplying 9 by 13.6, we get minus 122.4 electron volt. Therefore, the doubly ionized lithium ion ground state energy is minus 122.4 electron volt. In part B, we have to find the photon energy which is required to excite the electron to the third level, and this energy is equal to the difference between the energy of the ground state E1 and the energy of the third excited state, which is E4. Here, E gamma, energy of photon, is equal to energy of the third excited state minus energy of the ground state. Now again we are going to use equation number 1. So we get E gamma is equal to minus 3 square multiplied by 13.6 electron volt divided by 1. Here we replace n by 4 minus 122.4 electron volt as it is already determined in the part A. So multiplying 9 by 13.6, we get 122.4. Taking square of 4, we get 16. Minus into minus is equal to plus 122.4 electron volt. By dividing 122.4 on 16, we get 7.65. Now subtracting 7.65 from 122.4, we get 114.75 electron volt. Thus, the photon energy is 114.75 electron volt. Now we are going to find the wavelength of the electron. So the relation of photon energy and wavelength is given by E gamma is equal to hc divided by lambda, where E gamma is the energy of photon, which is already calculated. H is the Planck constant, c speed of light, and lambda is the required wavelength of photon. Rearranging the above equation for lambda, we get lambda is equal to hc divided by E gamma. Plugging the values, we get lambda is equal to 4.136 multiplied by 10 to the power minus 15 electron volt second, which is the value of Planck constant, 3 multiplied by 10 to the power 8 meter per second, which is the speed of light, and 114.75 electron volt is the energy of photon. Here we multiply 4.136 by 3, so we get 12.408 multiplied by 10 to the power minus 15 plus 8 meters. As electron volt cancel with electron volt, second with per second, so we get only meter. In terms of nanometer, we can write this as lambda is equal to 10.8 multiplied by 10 to the power minus 9 meters. Using the prefix, lambda is equal to 10.8 nanometer. Thus, the wavelength of the photon is 10.8 nanometers. Now that we have solved the problem, let's now summarize what this result tells us in the context of atomic transitions. The ground state energy of the doubly ionized lithium ion is calculated as minus 132.4 electron volt using hydrogen-like system formulas. The energy required to excite the electron from the ground state, n is equal to 1, to the third excited state, n equal to 4, is determined to be 114.75 electron volt. The corresponding wavelength of the photon needed for this transition is calculated as 10.8 nanometer, which lies in the ultraviolet range of the electromagnetic spectrum. Thus, we explored the concept of ground state energy, photon energy, and wavelength. I hope this video clarified your understanding of these fascinating topics. Thank you so much for watching. Don't forget to subscribe to Physics Mathematics Hub for more videos like this. Hit the bell icon to stay updated on all our latest uploads. Until next time, stay curious, keep learning, and let's explore the wonders of physics and mathematics. Allah Hafiz.